Hello guys, it's Dimitri again, here with another video talking about hermiticity and average values. So first, I talked about hermiticity in the last video, I believe, where I talked about Hermitian operators. And I'll just give a big review on what they are. Oh wait, let me just say this. So as I said before last time, Hermitian operators just mean that if you were to do an integral over all space, that over two functions, let's say f and over to operate omega onto g, it will still equal to if the operator was on f. So that's the definition of Hermitian operators, and how you're gonna learn how to prove that in later on in the video. So we talked about physical observables, and physical observables are basically what you get from operators, either being average values or getting eigenvalues from eigenfunctions. So let's say average observables need to be Hermitian. To be Hermitian. So that means any value that you extract from an operator has to be, and that operator needs to be Hermitian for it to be a physical observable. And this physical observable could be, like I said before, expectation values or eigenvalues from eigenfunctions. So now the why. Now why is that? So let me give an example. So let's say you have an expectation value omega, right? To get the value of this average value, you need to integrate over all space, and you need to apply the operator here to the function, and that average value. And whenever you take an average value, like I said before, it's pretty much that I'm taking a measurement at each specific point and I'm averaging them. That's what I'm doing when I'm integrating over all space and applying the operator. So I'll just put that in the notes here. So that means that this is the average of many measurements. And because it's the average of many measurements, this has to be real. And it has to be real. Now, this has to be real. This has to be real because think about it. Why would a measurement be imaginary measurement doesn't make any sense. So it has to be real. And you know that it's real. If you apply a complex conjugate onto this, remember complex conjugates, they convert negative I to I. But since an imaginary number doesn't have any since a real number doesn't have any imaginary components, that means if you apply this, it would be the same as equaling to z. And this indicates this is real. Now what now we can now let's say we're trying to get the average value of omega, right? Now if we apply the complex conjugate onto this, then this will equal to over qt, and this would make this here. So complex conjugate, they cancel out. So there's no complex conjugate, but it applies to the one in the operator. Let's see. All right. And this proves that just give me 1 second, guys. Just gather my thoughts. This here proves that the operator that the average that I mean a observable or average value has to be real. So expectation value is real, and that means that the operator also must be Hermitian. So it doesn't matter where you apply the operator. Operator for observable must be Hermitian. Because this here is equal to this up here. Alright, now let's move on to the next section. So what you're going to learn to do in recitation is to find out if an operator is Hermitian, and these operators could probably be something like the derivative operator. And I'll show an example of it right now. So let's see, proving is Hermitian or not. So let's say we have we want to find out if a certain operator, the derivative operator, is Hermitian. So let's say, and then this is on, I'll just put this onto g of x. And we want to prove that this is true. Yep, and then g of x. So to do that, you would have to use something called the, if you guys know integration by parts, I talked about it before. So let's say we're trying to do integration by parts. So the rule is with derivative operator is you apply the operator, you like, let's say you want to do, like, remember u, du, dv, and v. So I want to take the derivative off of, I want to take the derivative off of g of x and apply it to f of x. So this is going to turn into a it's going to have a derivative on it. Now I'll just put these on the bottom too. So this will result in g of x, and this would result in f prime of x. So let's just start with this one here. So in this integral, we see that f of x. So we want to apply the derivative on f of x. So we put f of x here, and we want to take off the derivative in g of x. So we put g prime of x here. Take the derivative of g prime of x. We want to take off the derivative of g prime of x from the result of the operator onto g of x, and you want to apply it to f of x, so that way it's equal on the other side. So we put u into f of x and dv into g prime of x. Then we take the derivative of f of x, and we get f prime. That's what I meant. And then we get, if we take the derivative of g prime of x, you get g of x. So you do crisscross, and then you would see that it's a result, and I'll just remind you guys, u v minus v du. So then in this case, u would be f of x, and g of x would be, yep, this would be g of x. Yeah, g of x. And then we would do its bounds from negative infinity to positive infinity. And then this would be minus uv du, which would be g of x. And then it would be, let's see, oh, let me write f of, yeah, it's right. And this would be g of x, and we have f of x, which is in the complex conjugate, so it would be f prime of x, yeah. And then this would be in the complex conjugate. And then these, let's just assume that these are two arbitrary functions. So it'll be infinity minus, this would be, this just could be 0. I think it would be, okay, yeah, this would be 0. And then after, you would just be left off with negative dx. And let's get the operator out. So then we have d prime of x. Let's be on x. Now, from seeing this, guys, would this be a Hermitian operator? If your answer is yes, then you're absolutely wrong because of the negative here. Now, because of that negative, this can't equal to this answer up here. I mean, this would equal to this up here. So because of that, d of d of x is not Hermitian. And that should be it, guys. If you have any questions, just shoot me an email or just post in the comments, and I'll get back to you as soon as I can. All right, have a good one, guys.